how we can take functions and then we can break them down to a simple ones. Each one will be recognizable by the table. Incidentally, I found my table. It was under the scanner. It was kept left there. So we will find the function, break it down into simple functions, which we can recognize them from the table, from the Laplace table, very simple table. On one side, you have all the functions listed. On the other side, you have the S. So objective is to break down pretty large functions into individuals and then do the reverse transformation. For example, if a function is given in the form of f of s equal to 1 over s plus 1 plus s plus 2 over s plus 2 squared plus 4 squared. I mean, it's already done. It's a ready-to-go situation. We are not always lucky to get that. If that is done, then how do we get the original function off of that? Well, minus 1. This is the shorthand for reversing. It would be inverse of 1 over s plus 1, inverse transform of s plus 2 over s plus 2 squared plus 4 squared. Okay. Then we have to look up. There is a lookup for both of them. And this will be the f of t equal to. So you will go to the table. 1 over s plus 1. Please go to the table. So C table. That is, you have it in the handout. It's page 10 of 10. That one. So 1 over s plus 1 is resembling to 1 over s plus a, which we know. Right there, 1 over s plus a has the third one from the top, e to the power minus p ut. That's it. So we inverse transformed that part. Next. What about the inverse transform of this one? If you look up in the table, it is, let me count it, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. It's the 12th from the top, and its inverse transform is e to the power minus 80 at cos of omega t. This is your omega, that is your a, and this is your a. So you have to construct the function e to the power minus 2t, because it is e to the power minus at, cosine of omega t. Omega is 4t. ut. You can factor out ut together. E to the power minus 2t, cosine of 4t, ut. Finished. Laplace transform of the function f of s is found. A time domain function. You figured it out. But the trick is this. Nobody is going to give you the function all in one go, like nicely separated for you to find out in the table. It is your part to get it done or formatted this way. Usually, a function of s will be given to you in the form of numerator polynomial, denominator polynomial. Next, your job is to break it down into the following form. This is called partial fraction. So There are cases, 3 cases, when you have a single pole, real single pole. This is a complex pole because it is a -2 plus -4j here. SP1 and the 2 is -2 plus and -4j, complex pole, like a conjugate. And then you have multiplicity poles, s+1 squared, s+1 cubes, and so on. So there are 3 possible cases, which I have solved 3 kinds of problems, and you have no work problem on those. By reviewing all the solutions here, you should be able to do your homework problem. Okay, let us start with example 3, which is our case 1. It's basically algebra from now on. Okay, let us solve the problems. You don't need to write anything down because the problem is solved. I'm just walking you through the steps. So a function is given. Example 3. It's called, say, simplest case. Case 1. You have f of s equal to s squared 5s plus 6, and then you have s plus 4. Of course, you will not find that in the table at all, but you have to change it. The first thing that you will do is look at the denominator. It's going to determine what will happen. So this denominator can be broken down into s plus 2 multiplied by s plus 3. Okay, that's called lucky case because the poles are real. One is at -2, the other one is -3. Can I visualize what kind of a function is going to come out of it as a waveform? Look at the importance of poles. The poles will tell me, not zeros. The poles will tell me that this function eventually is going to contain some kind of a constant, e to the power -2t, some kind of another constant, e to the power -3t. How did I get that? I got it from here. S is equal to -2. -2 is at -8, so you post it there. So that is why they are called characteristic roots. These are called characteristic roots, -2 and -3. And s squared plus 5s plus 6, whatever is in the denominator, it's called characteristic equation. It determines the character of the waveform, known as the natural frequencies of the waveform. Okay, so let's continue. How do I proceed further? How do I get those constants, k1 and the k2? Okay, this act is called a partial fraction. So here's the procedure. Once you break them down, you will write that the function s plus 4 over s plus 2, s plus 3 must be equal to a, which is that k1, over s plus 2, b over s plus 3. Always, you will find values for a and the b, real values, that as numbers that can break down this function into that form. Remember, the degree of the numerator should be 1 less than the denominator. So degree of the denominator, its highest power, is a 1. The power of that is 0. In other words, we've got s to the power 0. So just a number. This is the simplest case. Okay, so how do you determine the value of a and the b? This is kind of the traditional way of doing it, but I will show you more systematic. We will become more systematic. So it says, to find a, multiply both sides with, to find a, multiply by s plus 2, whatever is in the denominator. So you've got s plus 4 here, s plus 2, s plus 3. You multiply by additional s plus 2. Multiply that by s plus 2, you get only a, because s plus 2 is cancelled. Multiply that by s plus 2, you get b, s plus 2 over s plus 3. Okay? Eliminate. This will eliminate. All right? Now, after doing that, substitute s equal to minus 2. Substitute s equal to minus 2. The one that you eliminated, s plus 2, find the root, plug it in here. Look what will happen. This is gone. S equal to minus 2 will make that term 0. You will have a. We'll make this one s plus 4 over s plus 3 for the value of s equal to minus 2. What is this value? This will be your a. So we substitute here. It will be minus 2 plus 4 over minus 2 plus 3. That's a. So you will get minus 2 over 1. Excuse me, you'll get 2 over 1. So a will be equal to 2. A came out. In order to determine b, what would you do? Look at the line. You follow exactly the same procedure. You will multiply to s plus 3 throughout. So s plus 3 will cancel this, s plus 3 will multiply this, s plus 3 and s plus 3 will cancel each other. Then you will substitute s equal to minus 3. Because you multiplied a by s plus with s plus 3, you put minus 3. This will drop out, b will come out. So here, you will have minus 3 plus 4, you will have minus 3 plus 2, and s plus 3s are canceled here. It will calculate for you the value of b. And the b turns out to be equal to minus 1 in this case. Okay, so we figured out what is a as 2 and b as a minus 1. It is actually that k1 is a and the k2 is a minus 1. Now, rather than writing, distributing, multiplying, canceling, we have got to make a habit. This is a much better way of doing it. Let me show you what is that. Here, if you want to determine for single poles, of course, if you want to determine a, you find, and this is your f of s, your f of s, you want to determine a is equal to limit of s plus 2 multiplied by f of s when s tends towards minus 2. It means what? Look at the function, remove that, and substitute s equal to -2 in the rest. What is the rest? This is the rest. This is the rest. You remove s plus 2 if you're trying to get the a, which is on the top of s plus 2. You will look at the go to original function quickly, mask this, or if you multiply to fs, of course, s plus 2 will cancel that s plus 2 automatically. But you want to do it faster, cover it, put s equal to -2 in the rest. And you end up having, very quickly, even quicker, -2 plus 4 over -2 plus 3, quickly, just 2. See how fast it is with very little steps? How do I get b? Fast method, b. Get limit of s plus 3 multiplied by fs. When s approaches to -3. Okay, this means in the original function, cover the s plus 3, pretending it has been canceled in the process of multiplication. Cover that, put s equal to -3 in the rest. So you will have -3 plus 4 over -3 plus 2. There it is. This is equal to -1. Finished. This is much neater. A and the b are called, generally in a mathematical term, they are known as residues. Residues of this complex function around the simple singularities. They call them singularities. It's the same thing as poles. So you calculate the residues of these singularities in the complex function, and that's it. Those are your a and the b. Now, what do we do with that? So we know a is 2, b is -1. Watch for inverse transformation. Then inverse of f of s, which it is the f of t, is equal to inverse transform of 2 times 1 over s plus 2. Inverse transform of 1 over s plus 2. We can recognize that in the table. It is 1 over s plus a, if you recall. It is the third one from the top. In the table, page 10 of 10, third one from the top. And then this one, b -1, so keep the -1 out. Inverse of 1 over s plus 3. Same thing. It's 1 over s plus a. So here's the outcome. -2 e to the power -2t minus e to the power -3t for that one. Finally, everything multiplied by ut, because each one has a ut. Those Laplaces are calculated single-sided, and therefore ut needs to be posted. This is single-sided. Okay. That is how to do the inverse Laplace transformation. Inverse transformation 101. That's the sequence of all. When you have single poles. Notice that if you had even multiple of single poles, as long as you are not duplicating, you should be very happy, because that will be the way of doing it. It doesn't matter what is the numerator. Simply, if you want to know the constant on the top of that, you remove it, substitute its value in the rest. Remove this, substitute the value in the rest. It's the next position, and next one, and next one, and next one. You can determine a whole train of broken functions, partial fractions, simplified. Each one has a unique transform, and if it is a single one, it must be all exponential form, e to the -at form. Very simple frequency, very simple function. Then combine them, and this is your function of time. Okay, there, that's the solution. So we're done with case 1. Now we go one notch higher. This is called, this was example 3. Example 3, okay, so we have now done with this. To find B, we did that, we finished, page 5 is done. We go to page 6, which is case 2, example 4. Example number 4, and this is called case 2. Case is 2, complex poles. Complex poles. This applies to a situation where the poles are not single, they are not real, but rather pairs, conjugate pairs. In order to make the problem a little worthy of, to have the weight of a real problem, I added one single pole to the whole thing. So let's look at the function we want to inverse transform. So find inverse transform. F of s is equal to, let's say, s plus 5. We've got s squared 4s plus 13 multiplied by s plus 1. Okay, there it is. Okay, we have the 0 of the function. 0 is minus 5. It's basically doing the nothing about predicting what kind of a shape it will. But I have one of the poles. See, s plus 1, one of the characteristic roots, they call it. Yes, this is s equal to minus 1. Well, that means your a is 1. So we must have something like a e to the power minus p in the composition of the actual time wave. There is a shape like that, which is fitting of an exponential. It is a decaying, must be decaying, because that pole is in the left-hand plane. It's here, minus 1. What about this one? So if you try to break this down into product of two parentheses, it won't be real. So this is going to be the complex one. Complex pole conjugate. Both are complex conjugates together. Okay, let me see. Now, this function here, okay. Components of this function are also telling me something, if I format it properly. As of now, I cannot see much how the shape of the waveform is going to be. But I know that because it is complex, it must be oscillatory and decaying. It must be. If there was no coefficient for s squared plus 13, it would be just sinusoidal forever, non-decaying. So this is the decay. Do you guys remember 2 zeta omega n and omega n squared damping? We used to have a damping. This has to do with the damping because your omega n squared is 13. So you must have a damping. If a damping is less than 0.7, the result is an oscillatory decaying wave shape. We will get there. So let's see how we will solve the problem. How do we partial fraction? So this is the technique for partial fraction. Step 1, get Fs into 2 functions, s squared 4s plus 13 and s plus 1. The s plus 1 carries a coefficient a, which we need to determine, a constant a. This one with a complex pole carries a b s plus c. A, b, and the c are constants or numbers. We are going to determine them. The best that we can, we need to determine them. Okay, how do we go and determine those? This gets a little bit heavier. In order to determine A, B, and the C, I suggest always do the one that has a single pole. We can immediately determine what is A, because A pertains to the single pole. So that's the weak point. We can break the problem. I wrote it for you in red, shortcut. So shortcut is what? Just like before, A is equal to limit of s plus 1, that's the pole pertaining to the A, multiplied by the original function, this big function, and set s to minus 1. Or in other words, substitute s equal to minus 1. What does that mean? S plus 1 multiplying fs. It means if I post an s plus 1, multiply both sides, s plus 1, that s plus 1 cancels this, you are left with s plus 5 over s squared plus 413. That's it. Substitute s equal to minus 1 in the rest. This will be the outcome. Minus 1 plus 5 minus 1 squared 4 times minus 1 plus 13. Work it out. A is 4/10. We got it. 4/10. Okay. So finding the others, B and the C. How do you do that? Okay. This is a quick answer. You know, it is a good thing that if you can go get A, and we could, because it's a single one, easy to figure. So we got that very quick. Now, in order to generally determine A, B, and the C, the classic way would be you will write here. Let's see. You will multiply both sides by a common denominator. This is the denominator of the first one, that is the denominator of the second. In other words, the product of these two is B of S. Denominator polynomial, right? So multiply both sides of the equation, f of s, and this one. What will you get? This is the equation. I'm going to multiply. S plus 5, s squared 4s plus 13, s plus 1. Okay, multiply. by the same thing in the denominator. S squared 4s plus 13, s plus 1, equal to, multiply this one by that, you will have a over s squared plus 4s plus 13 times s plus 1 over s plus 1, and then you will have b s plus c, which is that term, multiplied by s squared 4s plus 13 times s plus 1 again, divided by s squared plus 4s plus 1, plus 13. Okay, you will get all that. Now, look at the cancellations that I did here. On the left side and the right side. Cancel the like terms from top and bottom. So that term, this term, from the left side, you are left with s plus 5. From the right side, you are left with s plus 1 cancels this, but that remains. The second order here cancels that second order, but s plus 1 remains. Then distribute a's and s's together, here and here. I wrote the outcome for you. Remember that we don't have any more fractions, we get a line. So there is no room in here. I'm going to write it from the top. So this is what will come. After that cancellation, which is that big line right in the center, page 6, you will end up with s plus 5 on one side equal to a times s squared. Here, s squared 4s plus 13. And then you will end up with b s plus c multiplying s plus 1. Okay, this is the leftover for us, left and right. This came from the reduction in here because you multiply by that term. So everything is knocked out except s plus 5. On the other side, whatever was common in the numerator denominator, you canceled it. And this is what is left. Now, grouping. You need to group all the coefficients of the exponential, the polynomial on the left and the polynomial on the right. So this is what will come out of it. You will have s plus 5 on the left. On the right, you will have a plus b times s squared. You will have c plus b plus 4a s. Then you will have 13a plus c. Oh, check out. This is a second order polynomial on the right side, which came from those individual fractions. This is a polynomial on the left side. You don't see any power of s squared there, right? But pretend that there was a 0 times s squared in order to match both sides. Then the classic trick is keep matching the coefficients of the polynomials together. So match the highest square, the highest power, to this one. Conclusion is a plus b must be 0. Equation 1. Next, coefficient of s. It's 1s. Therefore, c plus b plus 4a must equal to 1, number 2. Next, 5 and that one. 13a plus c must equal to 5, equation 3. Here, you've got 3 equations, 3 unknowns. Solve them. So with this trick, even without, the first time when we calculated it, if you solve all these 3, which certainly it helps if you had A ahead of the time. You've got 3 equations, 3 unknown. If somebody gave you one of the unknowns, like a day before, it's much easier to solve that 3 by 3 because you have option of taking which other 2 of the 3 to solve. So here, our A is a 4/10. That's a short thing. We got it from the shortcut. Substitute A, for instance, here, you get C. C is minus 1/5. Substitute here as B. B is negative of A, so B is negative of that, minus 4/10. That's it. We got the A, B, and the C. You can check it. If you substitute these values back here, it will satisfy all of them. So in this way, A, B, and the C is calculated. Okay, so how far we have advanced as far as the operation is concerned. It's not over yet. It's not over. We just managed to partial fraction it. So you will go to the main problem that you had. You converted that into A over S plus 1, then plus BS plus C over the quadratic. Let me rewrite it with all the values of A. This is a time-consuming problem. It's not a very quick problem. You can't get the answers that quickly. Okay. So let us construct. We've got A, B, and the C. That means we have progress so far up to here. F of S is equal to 4/10, that was A, 1 over S plus 1, this is easy. And then we have, I will just shortcut that for you, minus 2/5 multiplying S plus half over S plus 2 squared plus 3 squared. This is that denominator. You must, after getting the A and B and the C, you must now change the format of that into S plus 2 squared plus omega squared. Why? Because we do have something like that in the table, in the Laplace transform table. It will be for you number, there it is. It will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Number 12 from the top. S plus A over S plus A squared plus omega squared. But the one that we have, gentlemen, has an S plus A. S plus A over this. This is the number 12 table. Number 12 in the table, that. But it doesn't look like this one. Why? Because you have S plus 2 plus 3, that's fair enough, can be done quickly. Just convert that into that. I'm not lucky to have this instead of half. If I had 2, I would consider myself very lucky, but it will not happen, no. So how do we proceed? from this point onwards. That's why I said this thing is algebra. You have to be good with the numbers. Look at the trick, very simple. You need to induce this term here. So I'm going to take that and convert it into s plus 2 minus 1.5, 1.5. Okay. Make sure that the balance is kept. S plus half is s plus 2 minus 1.5. It's the same thing. Then, partial fraction here. Taking that term as the common denominator to this component and that component. You're going to partition them apart with the denominator. The reason is, in the table of the transform, we do have a transform, which is a number at the top, and that number is omega. This one here, omega over s plus a squared plus omega squared. This one is another classic function, which is identifiable in the table. So that's the trick. That's what I'm going to do. I'm going to break this down. See how I will do that. So keep writing that down, 410. This is the easy one, which almost we're done with that part. Minus 2/5. Keep it out. Put them in eyebrows here. Write s plus 2 over s plus 2 squared plus 3 squared. It's the first half that you partition. The next half would be minus, minus half times 3 over s plus 2 squared plus 3 squared. Okay. Why I wrote half times 3? Because I'm trying to mimic this number which is there in order to come up with what is identifiable in the table. See, they are identical. Half wouldn't be enough. Half divided by this. So 3.5. In the meantime, I should not change the product. Half times 3 should be 1.5. I should keep the balance. Okay. We're ready to go to do complete inverse transformation. Here are your originals. The original of that is omega over s plus a squared omega squared. Look at the format. You identify which is which. Omegas. Original of that one is s plus a over s plus a squared omega squared. So one more step, we will get this result. F of s is 4/10 here. This will be, of course, a 2/5. 1 over s plus 1. This guy will be minus 2/5. S plus 2 over s plus 2 squared 3 squared. This guy will be minus 2/5 times a half. It will be 1/2. Okay, let's see. 2/5 times 3. This will be 5/10. Of course, 5 cancels that. 1/5. I think there is an error in here. This should be minus 2/5 times that. Let me just check quickly. minus 2/5. 1/5. Okay, here, please correct that on the file. It's just a number. This is minus 1/5. Times, the rest is correct. 3 over s plus 2 squared plus 3 squared. Okay, let me just very quickly check myself. That's 2/5 correct, minus 2/5 times s plus 2. That's correct. This one is, that expansion is correct. Minus, here, minus 1.5. Minus 1.5 is broken down to half times 3. That's correct. And 3 is there. Half is here. Half is 1/2. 2 cancels 2 minus 1/5. Actually, it should be plus 1/5. Yeah, I made an error here, please. And also plus. So, to cut this short, on your notes, on this handout that I gave you, I'm sorry, the last line is, everything is correct in place, except that the coefficient is plus 1/5 times, as opposed to minus 1/2. Minus 1/2. Cancel that and write this. Okay? So it takes, unfortunately, minor correction. It's towards the end of the problem. So we need to correct that. Let me make a note before I forget in my own. Okay, got it. So this is the correction. Correct there. And final step, inverse transformation. So you inverse transform f of s to its time. It's the answer, your f of t. Keep the number out. Inverse transform of 1 over s plus 1. We remember the e to the minus at. It was 1 over s plus a. It transformed into that. So inverse of that is going to be 2/5, or let's say 0.4 e to the power minus t. Inverse transform of this one is the e to the power minus 2/5, which is again 0.4 minus 0.4 e to the power minus 2t cosine of 3t. So this is the cosine, the damped cosine. Okay, that's the amplitude of the cosine. That's the frequency. So it's a frequency that constantly loses its amplitude. It's a damping. 0.4. And this guy is going to be plus, again, correction. It should be 0.2. 0.2 multiplied by e to the power minus 2t sine of 3t. Omega t, which is 3t. Everything multiplied by ut, the single-sided, one side. This is it. This is the solution to the problem. It's not that easy, you know. It takes effort to do that, and involves algebra. And you see how I made a mistake there. You know, I just made some mistake. Okay, so that's the way you inverse transform. It's called by partial fraction. And one final step, and we will get this thing finished. Yeah. Case 3, and that's my final part for the night. Let's take a look at that. Next week, I will do for you the properties of Laplace transform applied to circuit analysis, applied to differential equation, how to obtain S-domain transfer functions, which is the real thing that you need for the control engineer. This is definitely a foundation of everything. I'm telling you, this is very, very important. The only trick with this inverse transformation is the judgment about the denominator, the poles. Single poles, that's piece of cake. You know how to do that. When it comes to complex, it is involved. In the complex one, when you see a complex, the modes are going to be e to the power minus at cosine of omega t's mixed with k2 e to the power minus at sine of omega t. So the pain is to get those coefficients, k1 and k2, by slowly refining and coming forward, and of course not making mistakes like I did here, till you get k1 and k2. It's kind of, molding and shaping. It's just like working with the clay. You've got to shape it into the pot and then plate the pan, the two different things. Until eventually they become recognizable in the table, in this table. So this table is something that you should have it handy when you're doing Laplace transform. Now we do with the case 3. Case 3 happens to be kind of a little easier. Example 5. That is page 8 of 10. 8 of 10 in the lecture note that I send you. So this is our original. A function of time, say, has the following shape: s squared 2s plus 5 divided by s plus 2 multiplied by s plus 1 squared. Okay, the key is in that square term, which is said there are real, which is a multiple pole. So we've got one pole in the S domain at -2. We've got double pole at -1, twins. How do we tackle this problem? Step number 1, suggest a way to get the coefficients applied to this circuit when to that function when we partial fraction. Generally, you see that your f of s will be equal to, generally, single a over s plus 2. Next, you will have b over s plus 1 squared. Now, don't leave it there. It's not over. When you have a multiple pole, there are other terms that are existing. C s plus 1. The last one would be d over s plus 1 to the power 0, which is just 1. Okay? So nothing comes. Keep decreasing. So if you have a s plus 1 squared, keep going. S plus 1 squared, s plus 1, stop there. If you had s plus 1 cubed, it would be s plus 1 cubed, s plus 1 squared, the last would be s plus 1. Okay? So you list every possibility of descending powers of that parenthesis. This is descending power. Power 2, power 1 of the same. Okay? Agreed? That's the trick. That takes care of puts you into the right track. The next thing is algebra. How do I get A, B, C? What is the smartest way of getting it? The smartest way. So I wrote them in a shortcut. The simple form, s plus 2. It's easy. So to get A, get limit of s plus 2 multiplied by f of s, which is that log thing, this whole function, when s is minus 2, when s is equal to minus 2. So that says you multiply this by s plus 2, but instead of multiplying that one, the better one is here. S plus 2, when you multiply, s plus 2 is removed. Then you substitute s equal to minus 2 into the remainder. This is the remaining part. That divided by the parentheses. So minus. I put the numbers there for you to see what is happening. Minus 2 squared, 2 times minus 2 plus 5. That's what is on top. And it is minus 2 plus 1 squared. Okay, fine. There. Quickly comes out A is 5. This is checked. Okay. B. The coefficient of the highest can be determined pretty much the same manner. Multiply f of s by that highest power, s plus 2 f of s. So we are removing this double singularity from the function, s plus 1 squared. When s tends towards minus 1, we should get a meaningful answer. If you did that, you multiplied s plus 1 with the parenthesis, you remove the double singularity. Then remainder is this function, the one to the left. Substitute the value of minus 1. Minus 1 squared, 2 times minus 1 plus 5 over minus 1 plus 2. So I did that for you. Yes, it's correct. It's 4. I wrote easy. Yes, of course it's easy. Now, determining C. Okay. Why it is not going to work for this term? Why it is not going to work by multiplying everything with s plus 1 and trying to put s equal to minus 1 in the rest? It won't work. Unfortunately, I wish it would, but it won't. Because it's obvious. If you multiply by s plus 1, only one term will be canceled. So still, you have a singularity there, s plus 1. So if I substitute s plus 1 in there, it's going to be a number over infinity. That's not an answer. So it fails. It fails for the single ones. So remember, when you're writing it like that, this trick works perfect up to the second order. It's very practical. When it gets higher, there's another approach. It gets more difficult, or you can use the first one, which is take a common denominator, get the polynomial, and try to match try to match left-hand side polynomials together, it can solve, but it will take pretty much a long way to do that. However, there is another way, the smart guy's way, which you can solve. It is not classic, but it can be done. What is that? Here. Let's see what we have so far. We managed to get s squared to s plus 5, that function, s plus 2, s plus 1 squared. We managed to get up to a 5 over s plus 1. We figured b 4 over s plus 1 squared, c over s plus 1, which I could not get c by multiplying throughout with s plus 1 and trying to put, and then getting cancellation, and then try to put, s equal to minus 1 and solve it, because I would get infinities. And infinity here, s plus 1, when you knock this out, there's one term remaining. So you can't put s equal to minus 1. So what you did here is not going to work for that last one. How do you get that last one? Shortcut, the smart guy's approach. You see that? There are infinite numbers in the world. Get one of those numbers other than minus 1. This one is not mine, this is 2. Other than minus 2 and minus 1. Other than minus 2 and minus 1. So not those singularities. Any number that you wish. But of course, between all these numbers, you're not going to pick up the complex. Although it would work, but don't pick up the complex numbers. So we put some convenient number. What is the most convenient number we can put in here, other than a pole, a singularity pole? S equal to 0. Or any other number. What will happen? S equal to 0. This will be 5 over 2. This will be 5 over 2. This number will be 4 over 1. That number will be c over 1. Solve for c. That's it. From this equation, figure out how much is c. C is equal to minus 4. Now, we got c equal to minus 4 by trying s equal to 0. How about I try minus 3? I'm just trying to convince you that it will work. What about if somebody's choice was minus 3? Will this number be different? Let's check it. It's just a matter of substituting. Isn't that right? Let's say s is minus 3, say. S is minus 3. Second trial. Substituting here, it's a minus 3. Remember, minus 3 is not none of them. So it's different from minus 2 and minus 1. So the top will be, I'll quickly write it down. The top will be 9 minus 6, 5. This would be minus 3 and 2. It will be a minus 1. Minus 3 and that would be minus 2. Squared would be 4. This will be 5 over minus 2. It will be 5 over minus 1 when s is minus 3. This one will be 4 over minus 3 will be minus 2 squared root 4. 4 minus 3 and 1, that's 2. 2 squared 4, that's right. Minus 3, it will be c over minus 2. So let's do the calculation. 9 and 6, that makes 3. 3 and 5 is 8. 8 over 4 is 2. This is minus 2. Minus 5. 1 minus c over 2. So let's see. That is equal to here, minus 2 plus 5 minus 1 is minus c over 2. This is equal to 3 and minus 1, 2 minus c over 2 multiply, c is minus 4. Same result. Did you see that? So whether you put s equal to 0 or you put s equal to minus 3, you'll get the same outcome for c equal to minus 4. This is the beautiful thing about the rational function. That is how you can do it. You could also do it in a different way. I'm not recommending, if there are some shortcut smart way to do that. If you had even 3 of them, 3 unknowns, how could you get an equation? Well, try 3 numbers, like 0 and something else and something else and something else, substitute there, you get 3 unknowns, 3 equations, solve them, and then you can find all of them. But if you can get 2 of them fast like this, which I showed you in the progress, but why do it, a 3 by 3? You just spare the last effort, that substituting a random number. Keep that last effort for the last singled out unknown. That is smart. Okay, so we got our numbers. Here comes the inverse transformation. Yeah. The inverse transformation. So we got A, B, and the C. Okay, so we got finally our f of last name step. So our function f of s equal to s squared to s plus 5 over s plus 2, s plus 1 squared, broke down into 5 over s plus 2. It broke down to 4 over s plus 1 squared, and then of course a minus 4 over s plus 1. Now inverse transformation. So you do an inverse operator on each one, which is f of t is equal to 5. Inverse lookup of 1 over s plus 2 minus 1. Minus 1 means you're going backward. 4. Inverse transform of 1 over s plus 1 squared. And finally, minus 4, inverse transform of 1 over s plus 1. Look for the table. This is equal to 5 times e to the power minus 2t. That's number 3 in the table. That one, which is a square, please note, it is 1, 2, 3, 4, 5. It's the 6th one in the table, a being equal to 1. So it is 4 times the multiplier, t e to the power minus t. This one is again same kind as that one, minus 4 times e to the power minus t, everything together because it's a right-sided function. Here is your time function solution. That's it. Do you have any question on this? Are you guys okay? Okay. Next time, this is what I'm going to do for you. I'm going to utilize the properties. Here. What is the Laplace transform of derivatives and derivative of derivatives? Laplace transform of integrals. And also apply it to the circuit analysis. We will have capacitor, inductors, and we are going to have Laplace impedances. And then we will be able to do a complete analysis of the circuit. Any kind of an input that you apply, it will be included in the whole function, and an inverse transformation of the whole thing will calculate or solve the circuit response, no matter what order it is, no matter what kind of an input you have, step input, constant input, or ramp, or sinusoid, whatever input you have, it will predict all of that for you completely, give you steady state value and the transient value. Laplace transform is the ultimate thing. It completely solves the circuit response. It's not just a DC response, although you can deduce DC response as well. There is a way from the properties. I will talk about it. Not only you can do the DC response, you can also calculate other things. Thank you very much. So this concludes today's work.
Thank you, Professor.
Oh, you're welcome. Okay. Thank you. Bye-bye.